how much charge is required for the following reductions. 1 mole of Al3 plus 2 Al. Let us write the reduction equation. Al3 plus 3 electrons gives Al. Here 3 moles of electrons are required for reduction. So quantity of charge required for the reduction of 1 mole of Al3 plus is equal to 3 Faraday. 3 Faraday, when we convert into coulomb, we can write 3 into 96,500 coulomb. That will be equal to 289,500 coulomb. 2,89,500 coulomb. Similarly, 1 mole of Cu2 plus 2 Cu. So Cu2 plus 2 electrons gives Cu. Here the quantity of charge required is equal to 2 Faraday, because here we have used 2 moles of electrons. So 2 into 96,500 coulomb, that is equal to 193,000 coulomb. 1,93,000 coulomb. MnO4 minus to Mn2 plus. The oxidation state of manganese in MnO4 minus is plus 7, because 4 into minus 2 plus x equal to minus 1, minus 8 plus x equal to minus 1, x equal to minus 1 plus 8, that is plus 7. So here the change in oxidation state is from plus 7 to plus 2. Here 5 electrons are added for balancing. So quantity of charge required is 5 Faraday. 5 Faraday, when we convert into coulombs, we will get 5 into 96,500 coulomb. That is equal to 4,82,500 coulomb. How much electricity in terms of Faraday is required to produce 20 gram of calcium from molten calcium chloride? In calcium chloride, calcium is in plus 2 oxidation state. So let us write the reduction equation. Ca2 plus 2 electrons gives Ca. Charge of 2 moles of electron, that's 2 Faraday. 2 Faraday will give you 1 mole calcium. That is, molar mass of calcium is 40 gram. That is, we will get 40 gram of calcium by using 2 Faraday. Therefore, to get 20 gram of calcium, we need half of it. That is, 1 Faraday will give you 20 gram of calcium. Then, second question, 40 gram of aluminum from molten Al2O3. In Al2O3, the oxidation state of aluminum is plus 3. So let us write the reduction equation. Al3 plus 3 electrons gives Al. So to get 1 mole of aluminum, we need 3 Faraday. 3 Faraday will give you 1 mole aluminum. 1 mole aluminum means 27 gram aluminum. So to get 1 gram aluminum, we need 3 by 27 Faraday. 3 by 27 Faraday. We need 40 gram of aluminum. So for 40 gram of aluminum, we need 3 by 27 into 40 Faraday. That is 40 by 9. That is equal to 4.44 Faraday. How much electricity is required in Coulomb for the oxidation of 1 mole of H2O to O2? So H2O gives 2H plus half O2 plus 2 electrons. So here the number of moles of electron used is 2 moles. That means 2 Faraday. So quantity of electricity required is equal to 2 Faraday. That is 2 into 96,500 Coulomb. 1,93,000 Coulomb. Second equation, FeO2 Fe2O3. That is 2FeO plus half O2 gives Fe2O3. Now let us write the ionic equation. The oxidation state of iron in FeO is plus 2. 2Fe2 plus gives, and oxidation state of iron in Fe2O3 is plus 3. So 2Fe3 plus 2 electrons. So for the oxidation of 2 mole of FeO, we need 2 Faraday. So for oxidation of 1 mole FeO, charge required is equal to 1 Faraday. It's half. A solution of nickel nitrate is electrolyzed between platinum electrodes using a current of 5 ampere for 20 minutes. What mass of nickel is deposited at the electrode? So, current is given as 5 ampere and time is given as 20 minutes, that is 20 into 60. So 1200 seconds. Then Q is equal to IT, that is 5 into 1200, that will be 6000 Coulomb. Now in NiNO3 twice, the oxidation state of nickel is plus 2. So let us write the reduction equation. Ni2 plus 2 electrons gives Ni. So 2 moles electron, that is 2 Faraday, gives 1 mole nickel. Molar mass of nickel is 58.7 gram. So 58.7 gram. 2 Faraday gives 58.7 gram. So we have only 6000 Coulomb. So 2 Faraday means 2 into 96,500 Coulomb will give you 58.7 gram. We have only 6000 Coulomb. So 1 Coulomb will give you 58.7 divided by 2 into 96,500 gram. Therefore, 6000 Coulomb will give you 58.7 divided by 2 into 96,500 into 6000 gram. So when we simplify, we will get 1.825 gram. 3 electrolytic cells ABC containing solutions of zinc sulfate, silver nitrate and CuSO4 respectively are connected in series. A steady current of 1.5 ampere was passed through them until 1.45 gram of silver deposited at the cathode of cell B. How long did the current flow? In silver nitrate, in silver is in plus 1 oxidation state. So Ag plus 1 electron gives Ag. That is 1 Faraday 96,500 coulomb will give you 1 mole silver, that is 108 gram silver. That is, to get 1.45 gram of silver, to get 1.45 gram of silver, the quantity of charge required is equal to 96,500 by 108, this is for 1 gram, then for 1.45 gram into 1.45. So when we simplify, we will get 1295.6 coulomb. This is the quantity of charge required for getting 1.45 gram of silver. Now, Q is equal to IT. That is, now we got Q. Now time is equal to Q by I. That is equal to 1295.6 divided by 1.5. That is equal to 863.7 second. Similarly, we can calculate for copper also. Cu2 plus 2 electrons give Cu. So 2 into 96,500 coulomb, that is 2 Faraday, will give you 1 mole of copper, that is 63.5 gram copper. So by using 1295.6 gram 6 coulomb, we will get 63.5. 63.5, if we divide with this quantity, we will get for 1 coulomb. Then for 1295.6 coulomb, we will get this much gram of copper. So when we simplify, we will get 0.426 gram. Similarly, we can calculate for zinc also. Zinc also, number of moles of electrons involved in the reduction equation is 2. So 2 Faraday, that is 2 into 96,500 coulomb, will give you 1 mole of zinc, that is 65.3 gram of zinc. So by passing 1295.6 coulomb, we will get 65.3 divided by 2 into 96,500 into 1295.6. That is equal to 0.438 gram zinc we will get. This question we can do in one more method, that is mass of substance deposited. So mass of silver by its electrochemical equivalent, that is atomic mass of the metal divided by number of electrons required to reduce the cation. Here the cation is Ag plus, so 1 electron is required for reducing it. So 1, that is equal to mass of copper divided by its atomic mass is 63.5 and number of electrons used for reducing Cu2 plus is 2 electron. So by 2 is equal to mass of zinc divided by atomic mass of zinc 65.3 divided by number of moles of electron used for reduction is equal to 2. Now, WAG by 108 is equal to, we can equate any two quantity, WCU by 63.5 by 2. Here mass of silver is given, it's 1.45. So 1.45 into 63.5 divided by 2 into 10 is equal to W copper. So mass of copper is equal to 0.426 gram. Similarly, we can equate WAG by 108 W zinc divided by 65.3 by 2. So W zinc is equal to WAG is 1.45 into 65.3 by 2 into 108. When we simplify, we will get 0.438 gram. Now we got the masses of all the metals. Now we can use the formula Q is equal to IT. So we have to find out the quantity of charge. From any one equation we can calculate the quantity of charge required. So 1 Faraday 96,500 coulomb will give you 108 gram. Therefore, for getting 1.45 gram, we need 96,500 by 108 into 1.45. So when we simplify, we will get 1295.1295.6 coulomb. Now 1295.6 coulomb is equal to 1.5 into time. So time is equal to 1295.6 by 1.5, that is equal to 863.7 seconds. Using the standard electrode potential given in table, predict whether the reaction is feasible or not. So the electrode potential of individual electrodes are given. We have to check whether the reaction is feasible or not. So first one, between Fe3 plus and I minus. So Fe3 plus I minus gives Fe3 plus will undergo reduction to Fe2 plus, I minus will undergo oxidation to I2. So this is the oxidation half reaction and this is the reduction half reaction. So A naught cell is equal to A naught cathode minus A naught anode. Here cathode is iron 0.77 minus 0.54. 541, so we will get 0.23 volt. So since we got a positive value, this reaction is feasible. Now second case, we have to check the feasibility between Ag plus and copper. So silver and copper, Ag plus Cu gives Ag plus Cu 2 plus. Now let us balance the equation to Ag plus. So Ag plus is undergoing reduction and copper is undergoing oxidation. So E naught cell is equal to, copper is undergoing, silver is undergoing reduction, so its value is 0.80 minus copper is 0.34 volt. So when we take, we will get 0.46 volt. Since we got a positive quantity, we can say this reaction is feasible. And third one, we have to check the feasibility between Fe3 plus and bromine, Br minus. So Fe3 plus will undergo reduction to Fe2 plus and Br minus is undergoing oxidation to Br2. So half Br2. Now Fe3 plus to Fe2 plus is the reduction, Br minus to Br2, that is oxidation. So A naught cell is equal to, reduction potential of iron is 0.77 volt and bromine is 1.09. So when we take, we will get negative 0.32 volt. So this value is negative, so not feasible. This is not feasible. Next we have to check the feasibility between silver and Fe3 plus. Ag plus Fe3 plus will give you Ag plus Fe2 plus. Here silver is undergoing oxidation and Fe3 plus is undergoing reduction. So E naught cell is equal to E naught of Fe3 plus, that is 0.77 minus silver is 0.80. So this quantity is a negative quantity. So this reaction is not feasible. Next we have to check the feasibility between bromine and Fe2 plus. So half Br2 plus Fe2 plus gives Br minus plus Fe3 plus. Here iron is undergoing oxidation and bromine is undergoing reduction. So E naught cell is equal to potential of bromine is 1.09 minus 0.77. So we will get 0.32 volt. So this is a positive quantity. So this reaction is feasible. Predict the product of electrolysis in each of the following. An aqueous solution of silver nitrate with a silver electrode. Here in solution we have Ag plus and H plus. The reduction potential of silver electrode is higher than that of H plus. So silver ions are getting reduced in preference to H plus ion. So we will get silver at a cathode, and anode also we will get silver. Silver anode will dissolve to form silver ions in the solution. An aqueous solution of silver nitrate with a platinum electrode. Here the platinum is an inert electrode, so it will not involve in the reaction. Then in silver nitrate, silver ions, and out of H plus ions and silver ions are getting reduced in preference to hydrogen ions. Its reduction potential is higher than hydrogen ion. Then when we compare OH minus and NO3 minus, OH minus ions are getting discharged in preference to nitrate ion. So we will get oxygen at anode because hydroxide ion will decompose to give oxygen. A dilute solution of sulfuric acid with a platinum electrode. Here also platinum is an inert electrode. So we have to compare H plus ion. Here in solution we have only H plus ion as cation. So at cathode it will get reduced to hydrogen. Then out of sulfate and hydroxide ions are having lower discharge potential compared to sulfate ion. So it will get discharged first and hydroxide ion will decompose to give oxygen. Next, an aqueous solution of CuCl2 with the platinum electrode. Here platinum is inert electrode. In solution cation Cu, we have Cu2 plus and H plus. So the reduction potential of copper is higher, so it will get discharged first in preference to H plus ions. Then in anode we have Cl minus as well as oxygen. From OH minus we will get oxygen, but we know due to over potential of oxygen we are getting chlorine at anode.